Imagine a world where things can pop into existence seemingly out of nothing and disappear just as quickly. Imagine a world where you can be everywhere in the universe at the same time, and yet nobody can know precisely where you are. According to our best theory of nature, the standard model of particle physics, this is exactly how the world behaves, because at its heart lies the strange theory of quantum mechanics.
Quantum mechanics took away all the certainty that classical mechanics had put into nature. In the classical world, everything goes like clockwork. If you know where everything starts and how it's moving, you can predict where everything's going to end up. Quantum mechanics has this concept of uncertainty built in.
We can't know anything with absolute certainty. We can only work out probabilities of different outcomes happening. We have a very hazy view of matter because quantum mechanics tells us that matter doesn't just consist of particles. Particles can also behave as waves. And it's a very confusing and non-intuitive way of looking at the universe, something that we're not really used to at all.
Now, quantum mechanics at first sight seems like a pretty strange view of the world, but it's experiments like this, the photoelectric effect, done at the turn of the 20th century, that forced us into that picture. Now, this is a gold leaf electroscope, and it's charged up. There's an excess of electrons on this plate, which causes the gold leaf to rise. Now, watch what happens when I turn a light on. The light forces the electrons off the plate, discharging it, and the leaf falls back down again. Now, that's pretty easy to understand. What isn't is that the energy of the electrons that come off the plate depends not on the brightness of the light, but only of the colour. Now, that is impossible to understand if you think of light as a wave motion, and it took Albert Einstein to come up with the correct explanation. He said that you can picture light as a stream of particles called photons, and not as a wave. And the energy of each photon depends only on the colour. That realisation, that explanation of the photoelectric effect, lies at the heart and at the foundation of quantum theory. Einstein's explanation of the photoelectric effect presented a new challenge to scientists. Up until this time, they had explained the properties of light in terms of waves. Suddenly, it seemed that light could also behave like particles. How could this be? The resolution to this seeming paradox had to wait for three of the giants of 20th century physics, Feynman, Schwinger and Tominaga. Working independently throughout the 1940s, they discovered a quantum theory of light, quantum electrodynamics, or QED. Where Einstein had explained the photoelectric effect in terms of particles, Feynman and his contemporaries went even further. With quantum electrodynamics, they provided a mathematical way to explain all the wave behaviour of light in terms of particles. QED was a major milestone in our understanding of nature.
I think Feynman referred to QED as the jewel of physics. Probably not because he invented it, but it explains all of physics outside the nucleus and excepting gravity. Okay, so it is a theory that explains the interactions of matter particles with one another via the electromagnetic force, and that drives all of physics and chemistry and material science. And so it's a theory of almost everything.
As well as explaining the behaviour of light, QED provided a revolutionary way to look at forces. Instead of thinking in terms of force fields, as Newton and Maxwell had done, QED explained the electromagnetic force in terms of particles. To understand how it works, imagine two electrons approaching each other. We know that they'll move apart because like charges repel. QED says that the repulsion is caused by a photon, a particle of light, being transferred between the two electrons. So the photon is the particle that carries the electromagnetic force. QED proved so successful that it seemed natural to look for quantum theories of the other forces that concern us as particle physicists, the weak and strong nuclear forces. By the mid-1970s, theorists had predicted that the strong force required 8 exchange particles called gluons, and the weak force required 3, the W+, the W-, and the Z. The problem was that these were just mathematical predictions, and as with everything else in science, if you want to be really sure about something, you have to see it. And to see it, you need one of these, a particle accelerator. Scientists have been building particle accelerators since the late 1920s. As well as letting us look at the structure of matter, they allow us to create hitherto unseen particles that our theories tell us should exist, like the elusive gluon. The secret to creating new particles lies in the most famous equation in science, E = mc². What this equation means is that mass and energy are interchangeable. Particle accelerators make use of this. They speed particles up and smash them together. The energy from the collision can turn into new particles. It was in 1979, when particle physicist still wore flares, that a brand new particle detector called Petra revealed the first spectacular evidence for a force-carrying particle besides the photon. The detector produced results like this, which could only be explained by the particle that carries the strong force, the gluon. The W and Z particles took rather longer to find. That's because they were predicted to be extremely massive, and we know from Einstein's E = mc² that it takes a lot of energy to make a lot of mass. So it took the biggest particle accelerator of its day, the SPS, and the most sophisticated detector of its time, this UA1, to coax them out into the open. But eventually they were found, force-carrying particles like the photon and the gluon, but with more mass than a nucleus of copper. The discovery of the W and Z particles was a triumph for particle physicists, because they now had a complete set of the force-carrying particles. But that's a long way from the end of the story. Why are the W and Z particles so massive when the photon and gluon are massless? The maths just doesn't add up as elegantly as we'd like, and we suspect there's a missing piece of the puzzle. In the early 60s, British physicist Peter Higgs came up with a way of generating masses for the particles that quite magically avoided the mathematical difficulties. Now, the Higgs mechanism is quite a complicated bit of physics, but we've had over 40 years to come up with good analogies, and here's one of the best. These are physics students. They represent the Higgs particles, filling every corner of the universe. If a popular lecturer like Fred walks through the students, they crowd around to ask profound and intelligent questions, and his path across the grass is slowed down. He has acquired mass. But if a less popular lecturer walks across the grass, then everyone ignores me. I'm a massless particle like a photon, and I can travel through the universe unimpeded at the speed of light. We don't know if the Higgs particle exists or not, but to find out, scientists have built the biggest particle accelerator ever. I'm standing 100 meters below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. Here, we'll recreate the conditions that were present in the universe less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? Well, you need one of these, the Large Hadron Collider. 27 kilometers in circumference and filled with over 2,000 superconducting magnets, each at 1.9 Kelvin. That means that they're colder than the space between the stars. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors.
The LHC is going to be exploring totally unknown territory, but that doesn't mean to say we have not got some ideas of what might be there. And one of the most famous examples is the idea of the Higgs boson. And this, according to theory, is a manifestation of what happened when the universe froze. Now, I don't mean froze like at ice temperatures, I'm talking about 10 with 17 zeros after it degrees. That before that time, according to our best theories, the universe was in a state of beautiful symmetry, whereas today it's full of structure. And just as the structure of the snowflake emerges when water freezes, so, in our theories, the structure of what we call the standard model of particles and forces emerges when the universe froze at this incredibly high temperature.
Why would we build all this to understand the universe? The universe today seems almost impossibly complex, full of planets, stars, and even life itself. But over centuries of experimentation, we found that the complexity is really a property of an old, cold universe. When the universe was much younger and much hotter, it appeared to be much simpler. And so it's here that we're going to recreate the conditions that were present in the very earliest times to hopefully reveal that underlying simplicity.
Well, speaking as a cosmologist, the LHC will be exciting because it should say yes or no to whether the Higgs boson, a type of particle, exists or not. And it's a sort of particle that cosmologists are interested in because we think particles of that type are responsible for a very rapid expansion of the universe in its early history, which forms the cornerstone of modern cosmology. It's a theory called inflation.
The standard model, our theory of particle physics that we have, tells us that there should be a Higgs and we should find it without trouble at the LHC. But our theory could be wrong. We know that our theory is incomplete, which means it has to break down somewhere. So if we don't find a Higgs at the LHC, it could be a sign that a new, deeper underlying theory of matter is just about to surface.
When you go to a new regime like the LHC will, quite often something pops up that's unexpected and can take physics down a different path altogether. And that's the sort of exciting physics that I'd like to see at the LHC.
Well, the LHC could find that there turn out to be more than 3 dimensions of space and 1 of time, and particles can actually disappear into extra dimensions, which is pretty wild and wacky, but it could be real science and not science fiction at the LHC.
I wouldn't like to predict what will happen at the LHC. It's like guessing what we'll find on our first journey to the stars. But the giants of history would have loved access to this machine because science is about exploring, and the only way to uncover the secrets of the universe is to go and look.